Welcome to the second lecture on solving second order differential equations using Laplace transforms. So the first thing I thought we would do is do revision of the stuff we did the last day. Okay, so first thing what we've got to do is look to Laplace transform everything. So I want to do the Laplace transform t squared y by dt squared plus 4 times the Laplace transform of dy by dt plus 5 times the Laplace transform of y equals 3 times the Laplace transform of e to the power of negative 2t. So remember we've got our initial conditions and all that kind of stuff, right? So we know that for this it's s squared ly. Take away s times 4, take away negative 7, plus 4, and then it's s ly, take away y0, which is 4, plus 5 ly equals, and I know I'm not going to fit it on that line, so it's going to be 3 times the Laplace transform of 1 over s plus 2 from the Laplace transform table. So remember, try and make your 5s look different if you can. I just kind of go over them double and try and make them look a bit bigger. Right, so that's s squared ly, take away 4s plus 7 plus 4s ly, take away 16 plus 5 ly equals 3 over s plus 2. Okay, so we now get our ly terms. That will be s squared of them, 4s of them, and 5 of them. And outside the bracket, or outside the ly terms, we've got negative 4s and s7, take away 16, take away 9. Like that. We take that across. So that's negative 4s, it becomes plus 4s. That's taken away 9, so it becomes plus 9. Okay, and remember, check and see if that bracket's exactly the same or looks the same as their question. Because if it does, you've probably done it right. Right, so you don't need to do this, but I think it makes it easier in these questions to make the right hand side one fraction. So we need this to have the same denominator. So we're going to make this s plus 2. So that means we need to multiply that by s plus 2 as well to keep it the same. Then I'm just going to multiply that bracket on the top. Just like that. Right. So we've got 4s squared plus 17s plus 21 over s plus 2, and I've still got this thing here. Let's move that over and underneath. Right, so that's us. Laplace transformed everything and then got it into one fraction, which is quite nice. So what I'm kind of looking to do every time. Right. Now, what I need to do is do partial fractions because you've got two terms on the bottom. But before I do partial fractions, I need to check and see if I can factorise that. Okay? So I'll look at it. A&M, that's a quadratic term. Can I factorise it? Plus 4, plus 5, 1 and 5, or negative 1 and negative 5. No, there's no way of making 4. So factorising doesn't work. So that means I've got to do partial fractions the way it is. Remember, you can check that by doing b squared minus 4ac if you want. Before the 5s and s's get incredibly annoying. Right, okay, so that can't be factorised, so my two partial fractions are going to be a over s plus 2 plus bs plus c over a squared plus 4s plus 5. You remember the degree in your partial fractions has to be one different between the top and the bottom, so that's degree 1, that's degree 2, so it was just bs plus c. Okay, so we do partial fractions now, so we multiply everything by the bottom. I'll put that in brackets. Right, multiply everything by the bottom here, so we get one linear equation. We get one equation. Okay, so the easiest way to deal with this is always to see, can I make any bracket 0? Well, that can't be factorised, so there's no value of s, so I'll make that 0. But I can't make that one 0, so when s equals negative 2. Four times negative 2 squared plus 17 times negative 2 plus 21 equals a negative 2 squared plus 4 times negative 2 plus 5 plus 0. That whole bit's going to be 0 because I've made that bracket 0. Okay. Can I get that to be 3? Okay, this here, that's 4, subtract 4, subtract 8, plus 1, plus 5 is 1, so it's a. So a equals 3 is what I'm looking for. Right, okay, now the next bit, what you could do is you could use two random values of s and end of simultaneous equations. I don't like that. I'm going to equate our coefficients. So that means I'm going to multiply out that whole equation there. I've just multiplied out this whole equation here. And then I'm going to look at s squareds. So s squareds, I've got 4 of them on this side, A of them on this side, and B of them on this side. So we're looking to compare the number of s squareds on the left hand side and the number of s squareds on the right hand side. Now, I already know that A is 3. So again, that tells me that B equals 1. Right, and then we can do whatever one you want. You can either use s's, you can use constant terms. I'm just going to do s because it's the next one. So 17 equals 4a of them plus 2b of them plus c of them. That should have been easier to use constant terms, but hey, who cares? Works out the same. 17 equals 4 times 3 plus 2 times 1 plus c. 17 equals 12 plus 2 plus c. So c equals 3. Right, so we've got our 3 values then for our partial fractions. So, and that was our partial fraction equation there. Okay, so I'm just going to swap 3 in for A, 1 in for B, and 3 in for C. Right, now they look to Laplace transform each part, but the thing I need to remember is because I couldn't factorise this bit earlier on, right, I know I'm going to have to complete the square. So let's get to that. So remember that's Ly. Right, so I need to inverse transform both sides. So L inverse Ly equals the invert 3 times the inverse transform of 1 over s plus 2 plus the Laplace transform, or the inverse Laplace transform of s plus 3 or s squared plus 4s plus 5. Right, now as I said already, I know from the fact I couldn't factorise that, put complete the square in here. So y equals, the Laplace transform of that's dead easy. It's just 3e to the power of 2t. Oh, sorry, negative 2t. Okay, because that changes sign. Right, just look at your Laplace transform table for that one. Right, now this is the more difficult part. I'm going to keep it like this at the moment. So that's going to be s plus 3 all over, and I complete the square in here. So that's s plus 2 squared, take away 2 squared, plus 5. And if you can't remember completing the square, I did it earlier on, and about 2 or 3 lectures ago, so we're going to have a look at it if you can't remember. Right, so that's me completing the square, finished, because take away 4 plus 5 is plus 1. Right, now I know that because I've completed the square, I'm going to have to use that first shift theorem backwards. So I know that in here I need to make everything that's got an s in it s plus 2. So I've got an s on the top, so I need to make that s plus 2, right? So s plus 2 and what gives me s plus 3? Well, plus 1. And that means that I've not changed the top in any way, right? Because s plus 2 plus 1 is s plus 3. And then my s on the bottom is also s plus 2. Right, now I'd use my first shift theorem. So because I'm using inverse first shift theorem, it becomes square brackets. And remember what I'm doing is I'm changing s plus 2's into s's. Okay, because that's the only way it matches a Laplace transform from my table. Because that's the way we always deal with the first shift theorem. Right, so that's going to become s plus 1 over s squared plus 1. Now, that nearly looks like the Laplace transform for sin or the Laplace transform for cos. But in the Laplace transform of sin and cos, I can't have an arrow subtract on the top. So what I'm going to have to do is split that fraction into 2 bits. Okay, so I can't have 2 terms on the top here. It's not in my Laplace transform table, which there we go. Look at my Laplace transform table. If I've got, there's nothing that's got a plus or arrow subtract in the top apart from this one here. And it can't possibly be this one because we don't have an s squared on the top. Okay. So so what I've done is split the top of the fraction, so I made it s over s squared plus 1 over s squared plus 1. Remember, you can always do that with the top of the fraction, you can never do it with the bottom of a fraction. Right, and if I look at the inverse Laplace transform of that, is cos 1t. I'm just going to put that as just to kind of, because that's, and the inverse Laplace transform, that's sin 1t, or just sin t, but I'm just going to write that just so you can kind of see where it's coming from. Because remember, 1 is 1 squared, so kind of looks like that, and then it matches this transform exactly. Right, now we know that the square brackets become e to the power of negative 2t from the inverse first shift theorem. That's cos t plus sin t. Now, that's also got an e to the power of negative 2t in it. So in order to finish it off, I'm just going to write it as e to the power of negative 2t 3 plus cos t plus sin t. Or you could write it any way you want, that would be perfectly acceptable as a final answer. But what I wanted to show using that example is partial fractions and inverse first shift theorem. Right, now I've given you a whole lot of questions to do yesterday. I've got more questions I can do, but what I'll do is I'll put up a revision sheet of those questions with answers again, and I'll do that later. I'll do that later today. Okay, so today's lecture we're actually going to look at is the last section on Laplace transforms, and as I've probably said to you before, the last really, really tricky thing we'll be doing in Engineering Maths 5. Yeah. So the Dirac delta function is used in engineering and other areas to model impulses or where a function is infinitely large for a very small amount of time. So this is very useful for approximating tall spike functions. So for example, this is your time. This is your timeline. You're going along, and then something really big happens at this point, and then it comes back down and back to normal again. So what I've said is it can be used to calculate the motion of a ball being hit by a bat in baseball. Okay, so you're going along, and then the ball suddenly hit, and that can model the energy that's going through the ball when it's hit, because it's hit and then it comes straight back down again. Okay, because it's only being hit for that very, very tiny part of a second, or very, very tiny part of time. Okay, so that's modelling the actual hit, the strike of the ball onto the bat. Okay, so that's what it's used for. It can be used in a whole lot of different electrical pulses and impulses as well. Okay, if you're not sure, then ask one of your electrical lecturers, because they know more about this kind of stuff than me. Right, so t is the time at which the impulse starts, or capital T, so that's the time at which the impulse actually occurs. So as I said, you're going along, the ball's hit with a bat here, and that's in motion, or that split tiny bit a second where the bat makes connection with the ball. Then we just go back, and now the bat's no longer making connection with the ball. Now, note the area under this curve. I know it doesn't look like a curve, it looks like a line up, but it's actually a really tiny curve. It goes to infinity, or goes towards infinity, is 1 unit squared. Okay, so it's 1 unit. So although it goes to infinity, the area under the curve is 1 unit squared. Right, now the Dirac delta function is denoted using this notation here. So it's got this weird curly D, where t is your time variable. As you can see, this is our timeline, which is our variable, which it has been throughout all Laplace transforms. And this capital T here is the time at which our impulse or our weird event happens. It changes something radically. Okay, now what we can use this for is the majority of the time that an impulse will radically affect something for a split second and then completely alter it for the rest of the time journey. So that's what we're going to model using this Dirac delta function. Right, now in order to use the Dirac delta function, we need to use a second shift here. Or some people might know that as a second shifting theorem, whatever you want to. This is the maths bit. So if f of t is 0 for any point in time before another time a, right? And then is this function g for any time after this time a. A is where this thing occurs, and that continues to affect it all the way along past its time. Then the Laplace transform of this function is e to the power of negative sa L g of t take away a. And sometimes that whole thing is just known as capital GS. But I'm going to keep it, I suppose, Okay, so if I've got a function g and s, and I want to go back to there, then I've got to use an inverse second shift theorem. Right, now it looks really complicated, but I'm just going to explain what it means. Right, now we're going to be using this and going back to here rather than all the way around for the majority of the stuff that we're doing. Right, so if, all this means is if we have exponential and s multiplying a function, we can find the inverse Laplace transform of i.e. a function in S then f of t is 0 everywhere before time a, and the inverse Laplace transform of our function at time at and after time a. Okay, so if we have an exponential in S, so multiplying a function that we want to find the inverse Laplace transform of, i.e. a function with an S rather than a function in t, then the inverse Laplace transform of that function, or f of t, is 0 everywhere before time a, and the inverse Laplace transform of our function at and after our time a. Okay, so I'm going to show you what that means, but I think it makes a lot more sense when I write it down in normal language. Right, but you'll see what I mean when I do an example. Right, so example 1. Find f of t. So that means find the inverse Laplace transform. F of s equals e to the power of negative 3s 1 over s squared. Okay, so this here is a function I can Laplace transform. Sorry, a function I can inverse Laplace transform. Right, and that's been multiplied by an exponential in S. Right, now our exponential has negative 3 in front of it, which tells me that a equals 3. So that's the time at which my impulse occurs, okay, or starts occurring. So that means that f of t is 0 everywhere before 3. Okay? So that's what that means. Now I need to work out what was in here. So the inverse Laplace transform of 1 over s squared is t. But this t, because of this 3 here, is going to t take away 3. So that means this is t take away 3 for every t greater than or equal to 3. And that's my answer there. Okay, so effectively your a always comes into our function. That's what it meant. This part of our formula, your t becomes t take away a. So our t became t take away a. Right, I'll do another example and hopefully it'll become even clearer. So find f of t. So f of s equals e to the power of negative 2s over s plus 7. Now this might not immediately be clear that it's an exponential multiplying a function that you can inverse Laplace transform. But you can rewrite that. As soon as you see s, you know, and you want it to be t, you know you've got to inverse transform. So I could rewrite that as like that. Now, that's a function in s with an exponential, and that's a function I know the inverse Laplace transform of, or I could use my table to find the inverse Laplace transform of. Right, so let's find the inverse Laplace transform of this bit here. First thing I should take into account that tells me that a equals 2. Right, so the inverse Laplace transform 1 over s plus 7 is e to the power of negative 7t. But remember, my formula tells me that t always has to become t take away a in this second shift theorem. So that means that we've got so 0 everywhere before 2, right? And then this everywhere at and after 2. But remember that t has to become t take away 2. So that means that f of t I just multiply that bracket, so I get, that means that the function is, the inverse Laplace transform is 0 everywhere before 2, and the function e to the power of negative 7t plus 14 at anywhere at 2 or greater than 2. Lastly, let's have a look at example 3. As you can probably imagine, what I'm building up to being able to do here is finding the solution to a differential equation involving a Dirac delta function. So that's why I'm doing lots of inverse transforms, because we know that the inverse transform is the most important part of solving that differential equation. Right, so let's have a wee look and see if I can make this. Right, so that's e to the power of negative 4s times 1 over s squared plus 4s. Right, cool, so a is 4. Right, now I then need to find the inverse Laplace transform of 1 over s squared plus 4s. So I go to my table of Laplace transforms. Here we go. And remember, you normally you always look at the bottom of the function first, right? I'm looking for what s squared take away 4s. So s squared take away 2s. What am I writing? Apologies. Right, s squared take away 2s. So if I look at my table, there's none of these functions look like s squared take away 2s. None of them. So if I know that's the case, I know I've got to use partial fractions, or I've got to use completing square. So I'll look for partial fractions first. So I'll look for factorising, and I can factorise this bottom bit because they've both got s in them. Okay, so that means I now need to do partial fractions. Like that. So 1 equals a s plus 2 plus bs, which is probably what some of you are thinking about this. So I then need to make the bracket 0 if I can, so that's when s equals negative 2. Which tells me that b is negative 1/2. Okay, the other part I can make 0, I can choose s to be equal to 0. That tells me a is 1/2. Right, so I'm then got so I then need to find the inverse Laplace transform of this. Okay, so what I should be doing is to take those 2 halves out. I should have probably done that first, but I'll just show you that if you forget to do something like that, you can just do it in the next line. So that's really 1/2 times inverse Laplace transform of 1 over s, take away 1/2, multiply the inverse Laplace transform of 1 over s plus 2. And that there is just 1/2 multiplied by 1, that is a half multiplied by e to the power of negative 2t from my table. So really that line there is not needed, because I should have just went straight to there. But you can have both in, it's not a problem. But if I was doing this myself, I would just have went, right, I've now got that function, let's do the inverse Laplace transform of both bits. Right, so I've now got my inverse Laplace transform. So that means that my function is 0 everywhere until my time a was 4. So it's 0 everywhere until 4, and then it's a half, take away a half, e to the power of negative 2t for t greater than or equal to 4. So nothing happens all the way up to 4, and then this function happens at 4. So these Dirac delta functions are a really, really good way of modelling something that it isn't on at all and then turns on at a specific time. Nope, that's something out. Whoops, that there should have been as t goes to t take away 4. So that should be t take away 4 in now. Oops. Because as soon as I'm inverse Laplace transforming, I should have had that in. I suppose you could have it in both bits, but as long as you've got it somewhere. Okay, I'm going to do example 4. This time I want you to try this one yourself. So can you find... Now this question is on page 44 of your Laplace transform booklet, so, and it's question 1. And after this, I want you to try question 2 and 3 as well. Question 2 will give you the easy knowledge that you need to rewrite it as e to the power of negative 2s times 1. May help. Right. So, here we go. So, means I can rewrite this as e to the power of negative 3s 1 over s to the power of 4. So then that means I need to find the inverse Laplace transform of 1 over s to the power of 4. Okay? Now, I know s to the power of 4 on the bottom, which means I need to get my Laplace transform sheet out and use the one with this just s and a power on the bottom, which is this one here, which means that you need the factorial of 1 less than the power on the top, so that means 3 factorial. So that's what I need it to look like in order for me to use my inverse Laplace transform. So 3 factorial is 6, so I need to take a factor of 1 over 6 in order to make that right. That's just 1 over 6 t cubed. And remember, as t goes to t plus 3, oh sorry, t take away 3. You remember, that tells me that A. So that means that f of t is 0, anywhere before 3, and a sixth t take away 3 cubed anywhere including and after the point 3. Okay, so the answers to question 2 and 3 are on the back of that booklet. And what I will do next week is finish off Laplace transforms by using them to solve differential equations with these Dirac delta functions, and then I will move on to eigenvalues and eigenvectors, or possibly double integration. I've not decided. I think it'll be eigenvalues and eigenvectors though. So enjoy the rest of your week, and I will speak to you next week.